Hey everyone, and welcome back to The Explainer. Let's jump right in. Today, we're tackling Lesson 2, Count-Controlled Loops.
I want you to imagine, just for a second, telling a computer to repeat something, but only a specific set number of times. You don't have to watch it, you don't have to write the command 100 times. You just give it a target number, sit back, and let the machine do the heavy lifting. That is exactly what a count-controlled loop does, and honestly, it's a total superpower.
Section 1. The magic of loops. From repetition to efficiency.
Because without loops, coding would be ridiculously tedious. Think about doing this the old way. If you want a program to output the word hello 5 times without a loop, you literally have to type out the output command 5 separate times. It's messy, it's boring, and imagine if you had to do it 1,000 times. No way. But with a loop, you just tell the computer to count from 1 to 5, print hello, and move to the next count. It's clean, it's short, and it's infinitely easier to change later.
And this perfectly illustrates where loops fit into the grand scheme of coding. Every algorithm, no matter how wild or complex, is built from just 3 core building blocks. We've got sequence, which is just steps running one after another. We've got selection, making choices with if and else. And now we're introducing the third core tool, iteration.
Iteration is just a formal programming term for repeating a set of steps. Most of the time, we just call it a loop. It's basically taking a chunk of code and running it over and over again. Simple, efficient, and incredibly powerful.
Section 2. Visualizing the counter. How the loop knows when to stop.
So here is the big question. How does the computer actually know when it's done? We definitely don't want it looping forever and crashing our whole program, right? That's exactly where the counter comes in. A counter is just a variable that keeps track of how many times a loop has run. Think of it like a little internal tally mark inside the computer's brain. Every time the action repeats, the counter ticks up.
You just give it a starting number and an ending number. Let's say our target is 5. The loop counts each time it runs. 1, 2, 3, 4, 5. And when that counter hits the target number, it stops automatically. You literally don't have to do a thing. Let's trace how this actually plays out inside the machine. We start by setting our count to 1. Then we hit a decision point that asks, is the count less than or equal to 5? Since 1 is definitely less than 5, the answer is yes. So we output hello, we add 1 to our count to make it 2, and we loop right back around. It keeps doing this until the count hits 6. At that point, it asks, is 6 less than or equal to 5? Finally, the answer is no, and boom! The algorithm breaks out of the loop and finishes.
Section 3. Python and the range function. Translating pseudocode into Python.
Flowcharts and pseudocode are awesome for planning, but let's translate this into actual Python code. In Python, we use something called the range function to control how many times a loop runs. It acts as our built-in counter mechanism. So to do the exact same thing we just walked through, you type for count in range, 1, 6, and then on the very next line, print hello.
And now I know what you're probably thinking. Wait a second. Why does it say 1 to 6 if we only want it to run 5 times? Well, here is a slightly quirky rule in Python. The range function stops right before the second number, so a range of 1 to 6 will count 1, 2, 3, 4, 5, and then stop. It won't actually run on the number 6. It's a tiny detail, but it's super important to remember when you're writing code.
Section 4. Nesting decisions inside loops. Combining the building blocks.
All right, it's time to level up. This is where real programming magic happens. We're talking about nesting. Nesting is simply placing one programming construct inside another one, like putting a selection, an if statement, directly inside an iteration, a loop. This means that every single time the loop repeats, it can dynamically evaluate a choice.
Let's walk through an example. Say we have a for loop counting from 1 to 5, but inside that loop, we have an if condition. It checks if the current count is greater than 3, output the word big, else output the word small. Because we nested these together, the computer checks this logic on pass 1, pass 2, pass 3, and so on. It dynamically alters its output based on exactly where the counter currently is. Pretty cool, right?
But how does the computer actually know the if statement is inside the loop? The secret here is indentation. Indentation is literally the visual language of coding. Anything indented under the for statement gets repeated. Anything indented under the if statement only runs if the condition is true. If you mess up your spaces, the computer gets totally confused. Indentation shows exactly what sits inside what.
Section 5. Tracking with trace tables. Never get lost in a loop again.
I'll admit, nesting loops and if statements can feel a little overwhelming to keep track of in your head. But don't worry, I have a secret weapon for you, the trace table. Trace tables let us basically predict the future. Instead of trying to hold all those changing variables in our brain, we use a table to record the value of each variable, step by step, as the algorithm runs.
It's super methodical and really easy to set up. Step 1, you just create a column for every single variable in your code. Step 2, create a row for each pass, meaning each time the loop runs. Step 3, you literally just read your code line by line and fill in the boxes with how the values change.
Let's look at a trace table in action, tracking a running total. We start with our total at 0. The loop runs from 1 to 4. On pass 1, the counter is 1, and we add that to our total, making the new total 1. On pass 2, the counter is 2. We add that to our previous total of 1, getting a new total of 3. You just map it out, row by row. By the time we hit pass 4, we can clearly see the final predicted output is going to be 10. There's no guessing, no mental math gymnastics, just pure, tracked logic.
Master loops, master programming. The ability to control repetition efficiently is what separates messy code from brilliant algorithms.
I want to leave you with a quick thought experiment. Look around your daily life today. What boring, repetitive tasks would you completely automate if you could just write a count-controlled loop for them? Once you start seeing the world through the eyes of a programmer, absolutely everything looks like a problem waiting to be optimized. Thanks for tuning into this explainer. Keep coding, and I'll catch you in the next one.